Welcome to the Theory of Anything podcast. How's it going, Cameo?
Excellent. How about you, Bruce?
Good. So today's episode is one that we've been talking about doing, which is the Deutsch Proposition from Avengers. Really, it'll be about how would time travel really work in real life, which is kind of an interesting subject in and of itself. So I understand that you've been reading up on this subject.
Yeah. Well, there's some interesting articles, and then of course there's David Deutsch's own writings about time travel and many worlds that I think really nicely play into all of this.
Yes. So maybe let's just set a little context in case there's somebody who doesn't understand what we're talking about. In the movie Endgame, Avengers Endgame, Tony Stark says this line: quantum fluctuation messes with the Planck scale, which then triggers the Deutsch Proposition. Can we agree on that? So this statement is complete gobbledygook. It's a meaningless, they're using real quantum words like Planck scale and things like that, but it is not, none of it's real, right? And in fact, there is no such thing as the Deutsch Proposition. David Deutsch was thrilled that they mentioned him in Avengers Endgame because that made him now officially a part of the MCU, and he's now a comic book character. So he was like super honored that he's now part of that. You know, just as an interesting side note on this, Jeff Bridges I can't remember what the name of the character is, but he's in the MCU he's an actor who played a character in the MCU. He was the first bad guy that fought Iron Man in the first Iron Man movie.
Okay.
But Tony Stark refers to Fat Thor as the Big Lebowski, which is played by Jeff Bridges.
Oh, that's funny.
So Jeff Bridges is both an actor playing a character in the MCU and is himself in the MCU as himself.
Oh, that's super cool. That's just clever writing.
All right. So there is no such thing as the Deutsch Proposition. So why did Avengers, the Russo brothers, the writers, why did they include Deutsch's name, David Deutsch's name, and make up the Deutsch Proposition as part of their plot line? So that's really what we're going to talk about. Now, the most obvious thing would be, David Deutsch is a famous scientist, world famous scientist. He's the one who his paper was the one that invented quantum computational theory. To some degree, it would just make sense to reference him in the same way it might make sense to reference Stephen Hawking, who also got referenced in the MCU.
Sure.
In the first Avengers movie. So to some degree, that might just make sense. But since you've been reading up on this, you're aware that there's almost assuredly more to it than that there's a specific reason why they decided to reference David Deutsch in Avengers when talking specifically about time travel. So
yeah, well, and it's specifically because of the way that Deutsch talks about time travel and the way that his many worlds
interpretation,
I was going to say theory nicely answers a lot of their plot problems.
Right.
Because they had a plot problem. They needed to fix all of the things that had happened with the ring, and so they really needed a way to have a new universe where everybody hadn't died.
Right. So now it's interesting. So why was David Deutsch referenced? Well, first of all, he has a 1991 paper called Quantum Mechanics Near Closed Time-like Lines, which is a technical paper that's about this subject that matched fairly closely to what they were trying to solve plot-wise. And then in The Fabric of Reality, which is the book you're currently reading, chapter 12 is the time travel chapter, which is a layperson version of that paper.
Layperson is the right word too, because it's a very enjoyable read, and it doesn't make me feel stupid. And I suspect that paper I wouldn't really even be able to read.
Yeah, I can't read it, and I'm like studying machine learning and
smart things.
Right. And so, it's one thing that I actually find interesting. Roger Penrose, another one of my favorite authors. I think I mentioned this in another episode somewhere, but he says that when he is looking at papers and looking at mathematical formula, he can't read them either, even though he's this world famous physics mathematician. I mean, he's specifically mathematical physics, right? And he says, I just try to get the gist of what the formula is trying to say. So it's interesting that, you might think scientists can just read scientific papers, but they can't either, right? I mean, they have to sit down and study them and slowly figure them out because they're hard for everybody.
Oh, well, that's comforting, I must say.
Okay, so let's talk about the plot point that kind of led to them wanting to use Deutsch. Now, the issue here is that everybody had been snapped by Thanos, so half the universe had died, and half the superheroes had died, and they wanted to bring them back, and they didn't know how to do it because Thanos, and in super cool, and I guess I should mention that we're going to have spoilers abound for Avengers in this episode. Super cool plot twist right at the very beginning where the Avengers get together to go take on Thanos, and you think that they're going to have this giant battle, and instead they find out he's can't do anything because he's nearly killed himself trying to enact his plan.
Right.
And he is trying to, he's just living on his own on a planet, and they kill him almost instantly. He's already destroyed the stone, so it doesn't do him any good. And then they have to just live with their failure from that point forward, which made for really interesting plot line for the rest of the movie. So when they start to raise the subject of time travel, can we do time travel? First of all, they lampshade it like crazy. They make fun of every other time travel movie in existence and how silly time travel is the way it gets treated in movies, right? Which I thought was hilarious.
Right.
But they raise the question, why not just go back in time and kill baby Thanos? Well, using time travel as it's used in every other movie in existence, you could just do that, right? Why doesn't Superman just go fly around the planet and set time back and just take care of absolutely every problem that ever took place by going back in time, right? And so they needed to address that, and Deutsch's view of time travel addresses that. It's impossible. You can travel back in time under Deutsch's view, but you can't change your present by going back in time. We'll explain why that is in just a second. But so that way you can't go back in time, kill baby Thanos, and just be done, right? So they're going to have to solve the problem in some more meaningful way, rather than just using time travel as a crutch to end the plot, also, so they don't have that problem going forward either. Once you've used time travel once to fix everything, then there's always the question of, well, why don't you just use it again?
Why wouldn't you just use it?
Yeah.
Right. Which is a fatal flaw with Superman always.
Right. Or for that matter, for Star Trek, right? I mean, the number of times they've traveled back in time to fix things, it's like, why don't they just do that for everything, right? So it's interesting that they decided to. Now, I should point out that they're completely inconsistent with how they handle time travel. So in Avengers Infinity War, Thanos, the Vision kills himself so that Thanos can't steal the stone. And then Thanos resets time and grabs the stone from Vision. So completely at odds with what they're now going to claim is true of time travel, right? And in fact, even in Endgame, Captain America goes back in time and then shows up as an old man, which you can't change your past through time travel, so that's impossible, right? So they only used Deutsch's views of time travel when it was convenient for the plot, and they ignored it in every other circumstance, which, that's what we would expect from a movie. So, but it was a really fun use of time travel. So let me kind of explain what is Deutsch's view of time travel. So in his chapter on time travel, chapter 12 of The Fabric of Reality, he uses virtual reality to try to explain time travel, which may seem really strange at first, but virtual reality has a very special concept in Deutsch's worldview. Because of the Turing principle, which we'll have as a separate podcast about, everything can be simulated on a computer, which means you can simulate all of reality in a virtual reality setting. And virtual reality for Deutsch would be kind of the matrix type, where you're directly putting impulses into the brain so it looks completely real, right? And you feel it, and it affects you just like a real world would affect you, the brain in the vat type situation.
Right.
And so virtual reality can also render things that aren't physically possible. You can have a world with different physics, like maybe you can travel faster than the speed of light in a VR setting, right? But everything that is physically possible is possible in a virtual reality setting. So the question he asks is it possible to simulate time travel in virtual reality, right? So it's a really interestingly posed question. Now, Cameo, have you gotten far enough in the book that you remember what his answer was?
I have not. I will admit, I have not.
Okay. So what he points out is that there's a bit of a paradox here. So let's say that, Cameo, I'm going to program for you a virtual reality setting so that you can go back in time and you can meet Caesar, as the example he uses, or just pick anything, right? Pick anything. If you could have a virtual reality simulation of time travel, what would you want to go see back in time?
Well, given right now and that we're living in the COVID world, I'd be really curious to go back to during the flu of 1918 and see how people were living. So that'll be my example.
Okay,
yeah.
So let's use that as an example. Okay, so you're going to go back in time in a simulation initially. We'll then ask the question of how does this apply if it's a real time travel. But I'm going to make you this simulation. So I've kind of got two choices at this point. One thing I could do is I could program a virtual reality setting. For the sake of argument, let's say that I come across some way to do a complete recreation of some part of the world, down to whatever level of detail we want, of what it was actually like. So you can't actually affect anything, but you're like a ghost and you're just watching what the world was like during the 1918 flu.
So like a holodeck on Star Trek, but without my ability to actually change anything.
Yeah. And for the sake of argument, let's say this recreation is 100% faithful, right? This is literally what actually happened, right? How I actually collect this information is besides the point. This is fiction. Okay. So you're literally getting to see what the past looked like. Orson Scott Card did a book about Columbus where they have a time machine that initially all you can do is go back in time and look at what things actually happened. You can't affect anything.
Yeah. Okay? What's the name of that book? I've read it.
Columbus, the Redemption of Columbus. It was Time Watch, The Redemption of Columbus.
Yeah, Time Watch. Yeah, awesome. Okay, yeah.
Very interesting book. And so they're just holograms in the past and they can go watch. And that would be awesome. Like imagine doing history where you could actually watch what actually happened in the past, right? And it's completely
it would change our understanding of the world.
Right. So it's completely faithful to what actually happened. Now, this really wouldn't be a very good virtual reality simulation, right? Because it's really just a recording. It's just a recording of what happened. That might be interesting in and of itself. But if I'm making a virtual reality simulation, what you really want is you want to be able to interact with the people and see and ask them questions and actually take part in what's going on, and so that you can actually really understand what's going on. And you would want to test to see if this is really a very accurate, do these people act the way they should for that time period? That would be how you would test the simulation to see how good it is, right? So what might you want to do if you had an interactive simulation that was a time machine? Going back to this time.
What would I want to do?
Yeah, like what would you do? You can go anywhere in the world. You're going back to this time period. What would you want to go see what it was like? What would you go do to see what it was like?
I would probably go to a city like San Francisco and, go to a fair or something to ask people how they were surviving, were they coming back out of their houses? Were they actually even locked in? And probably just ask them questions.
Right. So you'd want to interact with them. You'd want to interview them. That would be really useful for you to go back in time and interview them.
Yeah. Ask them questions, see what their life was like.
So now this creates a paradox, right? Because you weren't actually there back then. So the very fact that you're now there in this simulation and asking questions, by definition, makes it different than what actually happened.
Right, which is why in Star Trek they always try and avoid interacting with people when they're in the past.
Yes.
So that they don't break time or reality by, although they do it all the time, and it never seems to actually cause them problems. But.
Yes. Deep Space Nine did a really good one where Captain Sisko ends up being a historical figure because he accidentally gets a historical figure killed and then has to take over his legacy. So, so in fact, in Avengers, they laid out the rules of time travel in exactly that way. You know, no talking to our past selves, no betting on sports events, things like that, right? And yet, in a virtual reality simulation, there would be no need for you to not talk to your past self.
Right, because I'm not it's not real. So I wouldn't be impacting anything by interacting with people.
Right. Okay. So this is the paradox of simulation of time travel, which is if what you're looking for is a completely faithful image of history, it can't be a virtual reality simulation. It has to be a recording, right? But if you want it to be an actual simulation of the past, you have to be able to interact with it, which by definition means it's different than it actually was. Okay. Does that make sense?
Yeah, it makes perfect sense.
All right. Now, another thing that's interesting that he points out, and this one really kind of cracks me up, is that a time machine isn't a vehicle. It would be a special sort of place. There'd be like a passage that you would pass through and you would come out into a different time, right? And so you wouldn't actually like get in your DeLorean and travel through time in that. So maybe you would use a vehicle to go through the passage if it was like inside of near a black hole or something like that. But a time machine is actually a closed time-like line, okay, which is part of the name of Deutsch's 1991 paper. This is something that actually comes from Einstein. So in Einstein's equations, time travel is an open possibility. I don't know if people realize that, right? There's different ways to solve Einstein's equations, and some of them allow for time travel. But it's not like you travel in time. It would be certain areas where times meet up physically, because time is just a fourth dimension in Einstein's theory. Right?
Interesting. Okay.
So there might be like a wormhole or something that you could travel through that would take you to a different time and back, right? Because the times are touching at that point. And so it wouldn't be the way it's portrayed. And they kind of did this in Avengers. So the idea in Avengers, the quote physics that they use, is that there's this special place called the quantum realm, which right off the bat goes against Deutsch's theories of quantum mechanics, because under Deutsch's many worlds, everything's the quantum realm. There is no quantum realm. We live in the quantum realm every day.
Existence is the quantum realm.
Right. Which is actually what the theory says, right? But for various reasons, people have a hard time with that part of the theory, and they kind of make stuff up, and then it gets used for all sorts of things in movies, and the bar of reality is very, very low when it comes to quantum mechanics in fiction. And so they go into the quantum realm, and the idea is that there's no time in the quantum realm. So when you come back out of the quantum realm, you can, in theory, pass into a different time, right? This is
okay. It's like a doorway that I could use to get to a variety of other times.
Right. And this is kind of, it wouldn't be the quantum realm. There is no quantum realm. So there wouldn't be the quantum realm, which is the doorway. It would be using Einstein's physics. It would be using a wormhole or something like that, something near a black hole. You'd have to have some way where space becomes warped so that different times are touching together.
Right.
I'm like totally not explaining this well, because honestly, this just isn't something I fully understand, but I'm explaining as best as I know how. And so if for the sake of fiction, though, we're going to accept that the quantum realm is different than the macro realm, and that it's a place where time is different, and therefore when you go into it and then come back out of it, you can show up in a different time. Okay. So that was how they were kind of implementing Deutsch's view in Avengers. So
interesting. Okay.
now, when you come out in this, now here's another interesting thing about it. Stephen Hawking's had a party for time travelers. Are you familiar with this?
No, I'm not.
so he threw a party for time travelers, and then he sent the invitations after the party. And this was all over the news.
Okay.
And so no one showed up for the party, but now everybody knows about the party. And, presumably he's a famous enough figure, and this made the news media that if someone was in the future researching time travel, they would find this reference to him, and then they would have incentive to go time travel and come to his party, right?
Sure.
And so the fact that nobody showed up, he took as experimental evidence that time travel is not possible.
Which is a little bit faulty science on his part, because there's lots of reasons why they might not have come beyond just, beyond, I mean, not that I believe in time travel, but.
So, and he admits this, he says that there might be other, so it's not definitive proof. Nothing in science is definitive proof, of course. But you can kind of see his reasoning that he was trying to use his own celebrity as a way of testing for the existence of time travel.
Yeah, absolutely.
Now, here's the thing that's interesting. Deutsch points out exactly why nobody showed up. So if time travel does exist, and in our future, our future selves are going to build time machines, you can only time travel back to the creation of the time machine because it's a special place, right? And so from when the time machine is built, that's when you can start to have time travelers come through. But they can't come through prior to the time machine being built. The only way a time traveler could, since we haven't invented time travel yet, the only way a time traveler could have shown up to Stephen Hawking's party would be if somebody from the future had access to alien technology that had built a time machine way back into our time, or if there was some naturally occurring one like near a black hole or something.
Interesting.
Okay. So in fact, we know the answer to why nobody showed up to Hawking's time travel party. It's because we haven't invented time travel yet. So it doesn't actually show anything at all, because it will really depend on whether we can or can't build time travel. So Deutsch is very careful not to claim we can build time travel. We really would probably need like a quantum theory of gravity to be sure that if we could or not.
Right.
But he does point out that Einstein's theory allows for it, and quantum mechanics does not disallow it, and in fact makes it non-paradoxical. We're getting to that.
Right.
Non-contradictory. So between the two theories, we actually have some fairly good reason to believe time travel may indeed be possible. So in the future, yeah.
But we still couldn't use it using what you've just said about David Deutsch's theories. We still couldn't use it to travel back in time, because we couldn't travel past when it was created. Yes.
So you build the time machine, and then from that point forward, you could travel back to the time of the creation of the time machine. That might be years later, right? Or decades,
right.
Centuries later. So you will be able to.
We couldn't go back to plague times and watch.
That's right.
Experience the plague.
You would not be able to. You can't go back and see the dinosaurs, for example.
Okay.
So that is a hard limit that our current understanding of the laws of physics places on time travel. It may well allow for time travel, but it's not going to allow for it in the ways we use it in movies. So it's got a hard limit on that.
So
now,
one question here, because I don't remember which book it was that I read, but it posited that even if we had time travel, it still would only allow us to travel backwards. We will never be able to travel forwards.
You probably have that backwards, because we can travel forward in time very easily today, right? I mean, you and I are constantly traveling forward in time. And when you go to sleep, you're effectively traveling forward in time. But then like think about like Einstein's theory with as you approach the speed of light, that's kind of a more obvious example of time travel, where
Right.
the person who's on the ship going near the speed of light is aging much, much more slowly than the people back on Earth. So
Sure.
they're very much traveling
Forward.
forward into time.
That's interesting though, because when people talk about time travel, that's not what they're talking about.
Right.
And even when they talk about going forward, it's more the Back to the Future kind of being able to jump forward 70 or 80 years, have some impact on forward events, and then go back and have that somehow have an impact on past events as well.
Right. Okay, so let's talk about that. Nobody considers forward time travel in any way contradictory or paradoxical, right? The idea, if I were to travel forward in time, there would be no need to, avoid bumping into myself, or there wouldn't be a self of me there because I would have been traveling forward in time. There's nothing about forward time travel that seems at all paradoxical or contradictory. And there's no question of, could you go do whatever you wanted? And would time stop you from doing so or something like that? Because forward time travel is really just what we experience all the time.
Interesting.
Right? So it's backwards time travel that gives people problems. And what Deutsch does is he points out that there's no difference between backwards time travel and forward time travel, that they work exactly the same. So going back to our virtual reality example, let's say that you are doing a simulation of time travel, and now we're going to follow Deutsch's actual rules, that there's a time machine, and this time machine, you just finished building it. And so now you're waiting to see if a version of yourself from the future comes through to visit you or not. And so let's say you decide to enact a paradox. You say, okay, I am absolutely going to go through this. So the time travel machine is a doorway. Like think of it like maybe one of those revolving doorways, and you go through and come out at a different time. I think that was the example Deutsch used. So if you go through it, you'll go backwards in time, 5 minutes, let's say.
Okay.
So you're waiting to see if a version of you from 5 minutes in the future comes through the door. And you decide for yourself, if a version of me comes through there, then I'm definitely not going through and going backwards in time.
Okay.
But if no one comes through there, then I'm definitely going through, and I'm going to go visit myself 5 minutes in the past.
Okay.
So now this is starting to seem very paradoxical, right? It's like, okay, how does time travel stop you from just doing whatever you want and making it all consistent? Okay. So let's say that you do go through and you go back in time and you visit yourself from 5 minutes ago. The VR machine, what it would want to do is it would want to record what you were doing 5 minutes ago and then play that back. But the moment you go through, you can start to interact with yourself, and now you're going to be doing things you didn't actually do 5 minutes ago, right? So we're right back to that virtual reality simulation problem. If it's a real simulation, then it won't be faithful to what actually happened. It has to be a recording to be faithful to what actually happened. Okay.
Interesting. Okay.
And you can imagine also the virtual reality simulation. Suddenly, somebody comes through the portal. It's you coming through the portal. You're a version of yourself 5 minutes in the future, and it starts to interact with you, right? Well, you never actually went through. So, how does this virtual reality simulation know how you would react? Well, for the sake of argument, this is totally made up science fiction. It has access to your brain. It makes a copy of your brain, and it is a computer simulation of you, but one that is completely faithful, that is now the person who comes through the simulation and starts to interact with you.
Well, that's some complicated made up stuff.
Yes, it is. So you start to interact with yourself. You can probably tell it's you, right? It's you start to talk, and this other version of Cameo acts like you, knows what you know. You can ask her questions. She's you, right? She has a faithfulness that is, down to the neuron, the same as you.
Right. I can interrogate her about some secret part of myself that nobody else knows about.
Right. Which you've got plenty of those. So that'd be really easy for you to test.
Right.
Okay. So that would be how a VR machine would simulate time travel. notice that it doesn't actually constrain your behavior in any way. But it wouldn't be a faithful recreation of what you actually did 5 minutes ago or what you're going to do 5 minutes in the future. It would be one possible rendering of what you might have done in the past or in the future. Okay? And essentially what it is it's a parallel world. Now, many worlds quantum physics is very specifically about parallel worlds. So if we accept quantum physics as a good theory and we follow it through to its ends and accept the many worlds version of it, the parallel worlds version of it, which is really the only version that there is, then if you were to travel back in time, you would be traveling back in time to an instant that you were there before. But from the moment you arrive, you have changed things. And what you're really doing now is you're traveled back into a parallel world that starts at the moment that you're traveling back to, but from that moment forward, it starts to diverge from what actually happened.
I essentially created that parallel world.
That's correct.
By the act of going back, right?
Yeah. Yes. Now, I should point out that under quantum mechanics, when you take it seriously that everything is quantum mechanical, which is what many worlds does, that this is what happens in quantum mechanics all the time. Are you familiar with like Schrodinger's cat?
Oh yeah, sure.
Okay, so the idea is Schrodinger. I'm not even sure I'm pronouncing his name right. He was actually using this example. It's a famous example that he came up with. He was trying to show that there was a problem with quantum mechanics, that quantum mechanics didn't make sense. But today, it's such a well-tested theory that people actually take his supposed counterexample seriously as something that actually happens. And the idea here is we really kind of want to make, if you don't accept many worlds, then what you really want is you want to believe in a quantum realm. You want to believe that quantum mechanics is for microscopic things. But when you come into the macro realm, the quantum effects disappear. And in the macroscopic realm, there is no quantum effects anymore. Okay, and that's what Avengers is trying to do with its quote quantum realm, right? Is that it's really only at the microscopic level that the quantum realm exists. Schrodinger's cat is an thought experiment that we could do in real life that proves that there is no such thing as the quantum realm, right? The idea is that you have some sort of atomic event, and there's some probability of this atomic event kicking off a neutron, or I can't remember the exact experiment. I should have researched it before the show. I didn't even know I was going to be talking about this. But it kicks something off, and because it's superpositions in quantum mechanics, it's a superposition. It both decays and it doesn't decay, right? With some level of probability, and both take place in quantum mechanics. So what he's doing is he's saying, based on that taking place, we're going to break a vial of poison that's inside a box with a cat. And so according to quantum mechanics, if you take it seriously, what happens is the vial of poison superpositions into both broken and not broken, and the cat superpositions into dead and not dead.
Right.
Okay. And so you have this cat that's in a quantum state of both being alive and dead. Okay. And then according to quantum mechanics, you go then and open up the box, and upon your observation, the whole wave function collapses, the Copenhagen version. And then you will, with 50% chance, you will see a dead cat, and with 50% chance, you'll see a live cat. Okay. And at that point, if you're accepting Copenhagen and not many worlds, that reality is now supposed to be the only reality.
Okay.
Well, what quantum mechanics is actually saying is that when you open the box, you superposition, and you get caught up into the wave function. And
makes sense.
There's 50% of you that now see the dead cat and 50% of you that now see the alive cat. And now let's say that you've decided that if you see the dead cat, you're going to go dancing, and if you see the alive cat, you're going to go out for dinner,
Okay.
So this one little quantum event, that the decay of an atom, is now going to be the determining factor of whether you go to dinner or go dancing. So under quantum mechanics, what happens is a superposition of you going to dinner and you going dancing. And what's really going on is that you're going dancing in one parallel world and you're going to dinner in a different parallel world. okay? Quantum mechanics very quickly and very easily scales up to macro events. And it does, little tiny things like this do have giant macro differences of outcome. And that's why parallel worlds has to be accepted as part of quantum mechanics to make sense of it. The Copenhagen version of it, where they try to say it's really just one world, leaves all sorts of inconsistencies. They call it the observation problem, as to when does the collapse actually take place? And then there's also the question of what is the collapse? And Copenhagen says there's no explanation for that. It's just part of how quantum mechanics happens to work, right? Whereas many worlds is trying to actually make sense of it and try to give an explanation as to what's going on, okay? We'll do like a totally separate episode on just quantum mechanics, and I will give much better examples of this, but this is probably off the cuff, the best I can do with Schrodinger's cat here. So the idea of us doing something or some quantum event taking place or us making a choice, creating a different reality is just a natural part of quantum mechanics, and time travel doesn't change that, right? So when you go back in time and you try to interact with yourself, there's nothing inconsistent about this. You just simply go back in time, interact with yourself, and of course that's not the you that was standing there and nobody came through the portal, and of course they're behaving differently, but it's just a parallel you. They've got as much claim to be you as you do, right?
Right.
We got branching worlds all the time in the multiverse, and all of them are you. It's not like there's one secret one that's you and the rest are clones, right? They're all you. And so that all you're doing is you're visiting yourself in a parallel world. And Deutsch points out that even though we have all these limitations around what we can do with time travel according to the laws of physics, there's some really interesting things that we can still do with it. Like if you had contact with the future through a time machine, it wouldn't be your future. So if they said, don't do X because we destroyed the world by doing X, there's no guarantee that they're right, that their theory is correct. And it may be that you can do X and not destroy the world. But now that you have warnings as to what might have gone wrong, you can put safeguards in place or something like that. So while they can't like send lottery numbers back in time to you, because lotteries create giant branches in the multiverse and you don't know which one you're going to wind up in, or you're going to wind up in all of them actually. So sending lottery numbers back in time is no good at all, right? It's no more likely to be correct than any other lottery number. But their knowledge is still probably useful, even if it isn't really about your future or your past, right? It's still, they've done more work, they've seen something, they've got access to knowledge that you don't have access to. That's probably useful, right? And he points out that you could imagine there's some sort of problem that we need to solve, and we need to run it on a bunch of computers, and there just aren't enough computers in the world to run the algorithm. We could like parcel it out across the multiverse, in time, all these different versions of ourselves in other universes in time, and we could all run the computer program simultaneously and then share information. And you could do computations that were physically impossible in the regular world, in a single universe view of the world. And Deutsch points out that this is actually what quantum computation to some degree actually is that it's actually parceling out the computation across the multiverse and then coming back with an answer. And that's why you can do things like Shor's algorithm in a quantum computer can do something like Shor's algorithm that can crack any encryption, is because it's parceling out the computation to crack the encryption across parallel worlds, then coming back with an answer. And so the computation that's being done is larger than the number of atoms in the universe, because it's sharing it across parallel worlds.
Right.
Yeah.
So do we get to do that with ourselves?
Yes, that's what he's saying. If we had time travel, at least, we could, like, let's say you're a scientist, you could both work on the same problem, or the future version of yourself could share their work that they did in a parallel universe to speed you along, so that in your universe it's happening sooner.
Right, which is, to call it time travel is I think, if that's what we're describing, that's kind of a misnomer. to call it time travel.
Yeah, Deutsch points that out, and he says, actually, it's not a misnomer because they have just as much claim to reality as we do. It is actually time travel. You are actually going back to a moment you were in before. It's just you're causing it to branch from that point forward.
Right.
So now here's something that's interesting. I wanted to quote, this is from Fabric of Reality. He talks about how if we did have real time travel, it would behave like our virtual reality simulation, where it would be different. It would be a parallel world. And he says, but that all the parallel worlds would have to connect up in consistent ways. He says, for example, if I am not going to use a time machine, come what may, then no time traveling version of me must appear in my snapshot. That is, no universes in which versions of me do a time machine can become connected to my universe. If I am definitely going to use the time machine, then my universe must become connected to another universe in which I also definitely use it. And if I am going to try to enact a paradox, then, as we have seen, my universe must become connected with another one in which a copy of me has the same intention as I do, but by carrying out that intention ends up behaving differently than me. Remarkably, all this is precisely what quantum theory does predict. So,
interesting.
Now, how does this work for Avengers? Well, think about how the Hulk goes back in time, and he goes and he meets the Ancient One before she dies and tries to get her to give the time stone up. Okay?
Right.
And the Ancient One says, no, I'm not going to give it to you because then we won't have the time stone and you'll be dooming our version of the universe. Okay. So they can't change their present or their future by going in the past, but they do change that parallel universe that they've gone into by going into the past. Okay. So they actually copied that much correctly in Avengers. And in fact, the whole, I'm making some assumptions here, but the whole Loki TV show, Loki died in the canonical MCU, but when they went back in time, a version of him escaped. That version of him is in a parallel universe. And now they can make a whole TV show. And I don't know if they'll stick with this or not. They may just decide to claim that he's back and break the rules of time travel. But in theory, he now exists in this parallel universe, and they can make a TV show about his exploits. And recall also that this is the younger Loki, so he's the evil Loki, whereas the Loki that died was the one that had actually stopped being so evil and was starting to come around as a hero.
Interesting.
Right?
Do you think that they will leverage the fact that he's evil Loki?
Oh yeah. They're gonna. I'm certain Loki is such a fun character, right?
Yeah.
And
and he's more fun evil than he is good. Way more.
Right. So yeah, the version of Loki that they're going to have in the TV show is going to be the mischievous Loki, right? It's going to be the fun, enjoyable version of Loki. So yeah, I think what we'll find is that he's like Loki was a few movies ago, where he's starting to do good things, but then he just can't seem to stick with it, you know?
Right.
And he's sometimes a hero and he's sometimes just not. And I suspect that'll be the version of Loki that we'll end up with in the TV show. I'm actually really looking forward to the TV show. And how do you pronounce his name? Tom Hiddleston?
Yeah.
He is such a great actor for Loki too.
He is.
I'm really surprised. You go ahead.
No, you. I've always been really pleased. I think he's one of their very best actors that they have.
He's probably the only really good villain in the MCU other than Thanos. Most of the villains in the MCU are actually fairly non-memorable. It's even hard.
No, that's an interesting point. That's it is fairly non-memorable villainy.
Yes. Which is one of the areas where MCU has been kind of weak. But Loki's a really big exception. In fact, up until Thanos showed up in Infinity War, he was the only. They make fun of this on the internet. They'll have like things where they talk about all the memorable villains from the MCU, and they'll go like Loki, and then they'll start showing the other villains. They'll go no. I guess it was just Loki.
Only Loki. That's awesome.
So the one from Civil War, Baron, I can't remember his name. He's really menacing and memorable, but he's like a cameo almost.
Yeah.
So But yeah, most of them, like I can hardly even remember them. Like the Jeff Bridges one, I don't remember his name. He's, and I could hardly care that he didn't ever show up again. It's so most of the villains are kind of one shots and then they're done. And that's it. So Loki's a notable exception. Is he was the villain in Thor, and then he becomes the main villain for the Avengers, and he just keeps showing up over and over again, and just so well done. I'm really surprised Tom Hiddleston hasn't had more leading man roles. He's got like amazing amounts of charisma. So
I still think that will happen. He is very, very well loved. Or maybe, and it's always hard to know what impacts how people get cast in things, or what kind of roles they have in front of them. Maybe he's not found roles that he wants to pursue. I don't know. It's interesting.
Yeah. And there's also the problem of typecasting. I don't know that that's happened in Loki's case, but I was just thinking about like, have you watched Star Trek Picard?
Yeah. Oh yeah.
So I loved that. I thought it had a fantastic ending, and asked all sorts of.
Don't spoil it. I have not watched the very last episode yet.
Oh, you don't know about Santa Claus saving the day. Yeah. So I was actually researching. You start to Google Picard and Patrick Stewart, and he got really strongly typecast. And I guess I hadn't even noticed it had happened because he had so many good roles after Star Trek.
Right.
But like X-Men, Professor X, that's so close to Picard, right?
It is, certainly.
And he was great in Charles Dickens' A Christmas Carol.
Yes.
And he's gotten a few really good roles like that. But considering what a great actor he is, he probably should have had a lot more roles available to him, but he was so perceived as Picard.
Sure.
They could only really put him into roles that our brains allowed, at least this is their perception. I don't know if this is actually true or not, but our brains allowed us to say, oh yeah, that's Patrick Stewart,
like he would make a fantastic villain, but he's never had a villain role.
Right. The lady who plays Deanna Troi, what is her name? I can't pronounce it.
Circus.
Anyhow, Deanna Troi, she said that she felt that Patrick Stewart made Star Trek: The Next Generation because he was a Shakespearean actor. He was the most professional of the actors. That he was an unknown at the time. He had been in Dune or something, and that was it. But he had done Shakespeare, and he was so professional with his acting that all the rest of them stepped up their game around him.
Oh, interesting.
And so she claimed that he made Star Trek: The Next Generation. And of course that like dominated his life for 7 years. Everything was Star Trek for him, right? Because it became such a popular show. And but yeah, so it's interesting that Patrick, I would hardly say Patrick Stewart has had a bad career, right? He's definitely gotten some really good roles and things like that. But he was to some degree typecast. So I wonder if maybe that's happening a little to Tom Hiddleston also, that it's just harder for him to find roles because he's so well known as one thing. It's hard to believe that that's as strong a factor for him than it would be for Patrick Stewart. But
it's definitely a real thing, especially for people who become, if their show becomes really, really popular.
Yeah.
But the interesting thing about Hiddleston is, if you see him not dressed up as Loki, he doesn't really stand out as he's not really reminiscent of Loki. He doesn't look a lot like Loki.
Right.
That is interesting. When this was also a very interesting, like, whole side of we're not talking about many worlds anymore.
Yeah, and I guess the last thing I would say about the Ancient One is that was why she made such a big deal about they needed to bring the stones back, right? So they're going to go back in time. They're going to grab the stones from back in time, and then they're going to return them to where they left them. And that is actually consistent with the Deutschian many worlds version of time travel. You could travel to this parallel universe back in time, grab the stone, use it in yours, and then go put it back. And the reason why the Ancient One made such a big deal about putting it back was so that their timeline didn't get destroyed, so that their parallel universe didn't get destroyed. I should also note, Star Trek used the many worlds version of time travel. The Star Trek, the movie, the more recent movie.
Yeah, the one with
Chris Pine.
Yeah, Chris Pine. It's how they got away with having a whole different time, a whole different reality than the one that we remember from having watched the TV series.
Right. So that way they can change anything they want, and they're not actually wiping out what already took place that in the shows we loved, right?
Which is I think in my mind still a better approach than the Star Wars. Let's just ignore canon. Let's just pretend like all these people haven't been paying attention for all these years.
Yeah, and it's interesting. They're starting to catch on to this idea of many worlds time travel as a way of dealing with plot devices like this. It also, just as a side note, Picard is specifically about in the first Star Trek movie with Chris Pine. In the future, Spock goes back in time, and he's followed by that Romulan back in time.
Yeah.
And the reason why he's after Spock is because he blames Spock for the destruction of his world because of the supernova, right?
Sure.
Well, that's where Picard picks up. So we have Picard in the original timeline with the event with the supernova and what happened in his world because of the supernova. And then you have the movies, which are backwards in time in a parallel universe that happened because of the supernova, caused the Romulan to travel back in time. So they have this single event in the original universe, the supernova, that now has caused these branching Star Trek worlds, and with different things taking place in parallel universes. And then, of course, Spock, the original Spock, the Leonard Nimoy Spock, he died in the parallel world. He went back and entered the parallel world, and he stayed there for the rest of his life. So he's not in the canonical, shall I call it, Star Trek universe anymore. So anyhow, and I also think this is one of the reasons why Many Worlds doesn't seem so crazy anymore, right? I mean, like when Everett first came out with his PhD thesis describing Many Worlds, it was, but for the fact that his advisor was Wheeler, who had a really strong reputation, it would have been completely perceived as crackpot science. Wheeler kind of advanced, even though Wheeler didn't believe in it, he advanced it as a good theory that wasn't crackpot science, and it kind of saved Many Worlds from just completely getting forgotten altogether. But it was ignored for decades. And obviously Deutsch has done a lot to try to popularize it. But the thing that's really making it more acceptable, I think, in people's minds is the fact that the media has picked up on it, and that it's starting to show up in movies and television shows, and it's being used for plot devices. And we almost just accept the existence of parallel worlds now because we've seen it so many times in the movies.
Right. That's interesting. Popularization through sci-fi.
Yes. And I had a friend at work who I was describing Many Worlds to, and he goes, "Oh, are you talking about alternate dimensions?" And like an idiot, I said no. And then I go, "No, I mean yes." The problem being it's got nothing to do with dimensions, right? Parallel worlds in real life have nothing to do with dimensions, but that's the way Hollywood has chosen to popularize it, as alternative dimensions, right? And so that's the way most people think of it, because they don't learn it through the science, they learned it through Hollywood. And so when he was saying parallel dimensions, he meant parallel worlds, but he just doesn't understand the difference in the terminology. And since I understood the difference in the terminology, I started giving him a scientific answer to what was really just a Hollywood question, and had to correct myself. Oh, no, I actually do mean alternate dimensions. So yeah, it's very interesting, and it'll be interesting to see. This is one of the reasons why I say I really think Many Worlds has only got a couple generations before it's just the accepted paradigm, right? It's already taking over. And since there's always going to be some scientists who say, you know what, I just don't accept what my teacher taught me, that it has no explanation. They're going to go out, they're going to research it, they're going to find Many Worlds, and then some percentage of them are going to then become advocates for many worlds. And so you're going to see slowly the number of scientists accepting many worlds grow until finally it reaches some point where everybody just accepts it because everybody else is accepting it. And at that
right.
point,
and all because of sci-fi and
all because of sci-fi. And it'll get taught in schools at that point. We'll just be taught there are parallel worlds, and your elementary school child will be taught there are parallel worlds, and science shows that there is. That it'll be taught the same way everything else in science is taught. And that's really what our future is going to look like. Give it another 50 years or so would be my guess. A couple generations of scientists. Is 50 years a couple generations of scientists? I'm not even sure.
I don't know that it would take that long. My guess is closer to 25. That's, or maybe 30, because in somebody's career is going to last about 30 years. But
good point.
Even now, you have, I think, that critical mass is starting to happen. Because because the kids that are in high school right now or in their beginnings of college have already been sucking from this bottle of belief.
Hollywood's version of it, right?
Yeah. All right. Well, this was a fantastic conversation, Bruce. I think this was very fun topics, and I think we've got some cool topics for future podcasts.
Yep. All right. As always, thank you, Cameo, for joining us, and we'll see you next time.
Have a great 2 weeks.
All right. You too.
Bye-bye.